Hi everyone, welcome to Gans Part 2. Uh, we're celebrating Gans Week in Deep Learning this week. The recitation on Friday will also be on Gans, and we'll also implement a few very simple Gans, and you'll get to see how what we're studying in the lectures translates into code. But to start off, a little preview of what we'll do today. We'll do a Gans recap, what we looked at on Monday, a little less brief, and then we'll look at certain training issues that we had begun discussing on Monday and certain techniques that people use in training and stabilization of GANs. We'll so we have lots of slides to go through today. Hopefully, I really want to cover WGANs, and if we get time, we'll look at the history of GANs and certain GAN architectures that are popular. One architecture I really want to cover is conditional GANs. It's very trivial, and it's apparently very useful, used in a lot of applications in GANs. Yeah, to start off with GANs recap. So what are GANs? GANs are generative models. By that, we mean we're trying to learn the underlying distribution from which our data set comes from. So VAEs do the same thing. GANs just do it a little better. And the adversarial component there is that GANs are made up of two competing networks who are adversaries of each other. And in their competition, we end up with something that's able to generate data from the same distribution that our data set is coming from, and the neural networks. And what can GANs do? Well, the most basic thing the GANs do is they generate data. So, and you could use that property for various things. One of the things that somebody asked a question about and was briefly touched on Monday was data augmentation. That's a very popular application of GANs. One of the projects last semester in the deep learning course was on using GANs for data augmentation. So there was a team that was working with healthcare data, and healthcare data, as we all know, is expensive, difficult to get. And what those guys did was I think they were working with MRI images, and they generated certain MRI images using GANs to augment their existing data set. And the combined data set improved the classification accuracy on the tests that they have. Another very popular application of data augmentation is something that's used in the industry. So companies have developers all around the world, but the privacy laws of different countries are different. So but these developers need access to data to create models, to build technologies around them. And since they cannot provide them with actual data, GANs or generative models are used to provide similar data so that they can work with it. Will not be as good, but it's enough to let them begin developing models and technologies around the company data. Other common things that people use GANs for are image-to-image translation, text-to-image synthesis, single-image super resolution, something a few of you are doing in Homework 5. One of the interesting applications I read about when I had just joined CMU, took the deep learning course in my first semester, and I really wanted to do a project on it, was one of Bhiksha's paper, where in the paper they generate faces of a person just taking their speech as input. And at that point, it was like my first month at CMU, I did not understand GANs too much. But what I was really surprised about was that the faces that were generated were so the GANs would get things right that surprised me, that the GANs would get the age of the person right. Like it would get the gender of the person right, not that difficult, but it would also get the age of the person right. Certain other features of how the generated person and the actual person looked like were also similar. So yeah, that was a wonderful paper. But yeah, these are certain applications of what GANs can do. And how we train a GAN, as I said, we have two components in GANs, a generator and a discriminator. At time t equal to 0, we input a latent vector into the generator, and it generates some data. At time t equal to 0, it's usually gibberish. The task of the discriminator is to guide the generator, provide feedback to the generator. The discriminator acts as a beacon of light, and the generator learns from it. So the discriminator's job is to quantify how good or bad the generator is doing and provide feedback, and in somehow uh, uh, back propagate its expectations to the generator, which the generator uses to learn. In terms of what these networks are, the discriminator is just a binary classifier which differentiates images in two classes, which classifies images into two classes: real data, which by definition is our given training data, and fake data, which by definition is anything that is generated from the generator. And let's go, I know we did this on Monday, but let's go through the drill again of how we train a GAN. My aim on Monday was to make the GAN, the different components in GANs and the training process more intuitive. But on Monday, I was asked a question. I don't remember the exact question, but what I heard was that the student did not have a clear intuition of the loss function of GANs. And my aim today would be to do that, is to provide an intuition of what intuition for the value function that we optimize, the min-max KM in GANs. So with that in mind, let's start with certain trivial questions. We have two components in GANs, discriminator and the generator. So can anyone tell me which of the two components do we train first?
Discriminator?
Yeah, we train the discriminator first, but with what training data?
I think with like real data or whatever garbage that the generator throws at it first.
Yeah, so the discriminator binary classifier, two classes, real and fake data. Real data, the data set that we have. Fake data is anything by definition that comes out of the generator. And yeah, and we generate data for the fake class, and then we use that data to train the binary classifier. And so the next thing we do is we train the generator, but what's our training objective when we do that? Yeah, so I'm seeing some answers in chat, is to try to fool the discriminator. That's exactly right. The objective of the generator is to generate images such that they're classified incorrectly by the discriminator. So everybody agrees to that answer, right? You're on the record saying that you agree to this, because the next questions I ask are not going to be a repetition of what we did on Monday, and I am going to hold everyone to this. So everybody agrees, right? If I hear no objections, I will move on. And yeah, just a little preview of what we do when we train GANs. We start off by training the discriminator using the current ability of the generator. That means we generate whatever images the generator can generate and use those images as our fake class data to train the binary classifier. Then we train the generator to beat the discriminator. By that we mean, so in some sense, the generator levels up in this scenario, and then the discriminator also has to go to the generator's level. So we train the generator gets better. So we also now have to train the discriminator so that it's also leveled up. And in this kind of competition between the two, we get a generator that is able to produce data from the same distribution that our given data set comes from. So let's begin a new set of questions, and hopefully my aim is to give you an intuition of the loss function of GANs. And what we'll be doing is coming up with a loss function of the GAN system that we looked at. So this is me setting up the problem for you, and then I'll ask you the questions as to what the loss function or what the different components of the loss function should be. So we have two networks in a GAN. The discriminator, whose output I represent by dx theta. Theta are the learnable parameters in the discriminator. And x is the input. So if the input if the images that our data set contains is say MNIST images, then x belongs to 28 cross 28 or a 784 dimensional vector space. Then we represent the generator by g z of theta. Z is a latent vector from a chosen vector space, sampled from usually a unit Gaussian distribution, unit normal distribution, zero mean, unit variance. The vector space dimension is a hyperparameter here. So the generator's job is in some sense to create a mapping between that latent vector space to the space in which our data set comes from, and also be able to generate data which is very similar to our actual data. P of T is the actual data distribution. P of G is the generated data distribution. Now, D of X, what does it represent? It represents the output of the discriminator, yes, but it also represents the probability that X came from the actual data distribution, PD. And GZ, what does it represent? It's the output of the generator, yes, but it's also a point from the generated data distribution, PG. So I hope this setting up of the problem statement is clear to everyone, because next I'll start asking questions about what we should do in different scenarios. So does anyone have any questions up to this slide or about this slide? Okay. Do we refine PG as we generate more data? Oh yeah, so PG is not fixed. That's a good point. PG is something that's changing with every iteration. It's whatever the generator can generate at a particular point in time, and it changes with every iteration. PD is fixed. So how do we train a GAN? So the problem statement setup is present here in case anybody wants to take a look. But my question to you is, if X, if X is a point which is sampled from the distribution, from the actual data distribution, how should the discriminator train, and what should happen to the value of dx? So in what way should the discriminator train, and what effect should it have on the value of dx if the input x belongs to the actual data distribution? Remember, dx is the output of the discriminator and the probability that x came from the actual data distribution. Yeah, so I'm hearing, sorry, I'm reading answers in the chat say it should be ideally 1. And yes, so basically what we're trying to say is that the discriminator should train that such that for a point x coming from the actual data distribution, dx should be maximized, which also means that log of dx should be maximized, which also means that the expectation of log of dx for a point x that comes from the actual data distribution should be maximized. And you can think of this term as the chances of real data being called real by the discriminator. And we want this thing to be maximized while we're training the discriminator. So everybody agrees to this, right? You came up with this, the answer to this. Manish and Sridhar said this. I did not. I just translated what you said into mathematically. So next question. Let's say now that X is the output of the generator, which means that X now is a point from the generated data distribution. Now, what should happen to the value of dx, or how should the discriminator train? And what should happen to the value of dx if X is a point from the generated data distribution, or if X is the output of the generator? Yeah, from the point of view of the discriminator, what should happen? Yeah, I'm seeing answers in the chat. Which are all correct, which basically say that dx should be minimized in this scenario. So again, you said it, not me. Oja said it, Manish said it, a couple of other people said it. So all I'll do now is translate to what you just said mathematically. What this means is that dx should be minimized, which means log of dx should be minimized, which means log of 1 minus dx should be maximized, which means that this expectation of log of 1 minus dx when x belongs to the generated data distribution should be maximized. And here I've just replaced x with g of z, which I mean is that x is now an output of the generator, and z is a point sampled from chosen prior in the latent vector space. And you can understand this term as the chances of fake data being called fake. And the discriminator wants to maximize the chances of fake data being called fake, right? That's exactly what you guys said. So in case that a data point comes from the actual data distribution, the discriminator wants to maximize this expectation if the data point X comes from the generated data distribution. The discriminator wants this term to be maximized. In overall, the discriminator wants this sum to be maximized. And this is what the training objective of the discriminator is, to maximize this sum, which is to maximize the chances of calling the real data real and the chances of calling the fake data fake. That's what the discriminator wants to do. Again, this is what you guys said, not me. Oja said it, Mani said it. So, and everybody agreed. It's on the record. So you cannot ask me questions of what this means anymore, because you said it. No, I'm kidding. You can still ask any questions that you want. What?
So Prerna has a question.
Yeah.
Can you go one slide on the next slide?
Yeah. Which one?
No, on the previous one where you mentioned about the dx log of dx.
Tell me to stop
Can you
when
go
I.
more? Yeah, this one.
Yeah.
So here dx should be minimized, and log of dx, log is an increasing function. So should not it be minus log of dx should be minimized?
No, log is a monotonic function. So
yeah.
Yeah, so whatever happens to dx happens to whatever you want to do to dx, do that to the log of dx as well. So if
Okay.
you minimize dx, so this is um once again, yeah. So so bad drawing, but this is kind of what the log function looks like, right? So if you are trying to minimize x, which means you're kind of trying to go back on the x-axis, which is the same as, so let's say this is 1. So at this point, the log, sorry, this cannot be 1. This is 1. But between 0 and 1, log is monotonic. Actually, it's monotonic everywhere, but also in our area of interest. So that means that if you want to minimize x, we are also, it will achieve the same purpose by minimizing log of x.
Okay, got it. Thank you.
Yeah. So slides are stuck. Get back. Yeah, so this is the objective, that this discriminator maximizes chances of calling the real data real, chances of calling the fake data fake. Now, given that, what should the generator do? And you've answered this question before. So you're on the record doing that the generator should generate images such that they're classified incorrectly by the discriminator. So what that means is, and let me know if you guys don't agree with this, what this statement, if I were to translate this mathematically, it means that d of g of z should be maximized. G of z is the output of the generator, and we want the discriminator to classify it incorrectly, which means that the discriminator should call this 1, which means that d of g of z should be maximized. And that's what the generator wants. Does everybody agree with that? Cool. I'm seeing a bunch of yeses in the chat. No objections raised, so I assume everybody agrees. So the generator wants that d of g of z should be maximized, which is same as saying that the log of d of g should be maximized, which is same as saying that 1 minus that should be minimized, which is same as saying that the expectation value of log of 1 minus dg of z should be minimized if z comes from the generative. So z now is a point from the chosen prior distribution in the latent vector space. And this is exactly the same term as this. So you can think of this as being, again, exactly the same as we called it here, the chances of fake data being called fake. What the generator wants to do now is to minimize that. It wants to minimize the chances of fake data being called fake, which means it wants to maximize the chances of fake data being called real. And it's the same as trying to minimize this term because the generator has no control over it. And in essence, the discriminator wants to maximize this value function, whereas the generator wants to minimize the same value function, where the first term is the chances of real data being called real. The second term is the chances of fake data being called fake. So this is the loss function that all of you came up with for Gans, not me. And let's see what the original Gans formulation says. Well, it's exactly the same thing. So good job, guys. Only if you were doing research in Gans in 2014, you could have come up with it yourself. Again, this is not to say that what they have is very trivial. It's just that it's very intuitive. And again, the first term is the chances of real data being called real. Second term is chances of fake data being called fake. The discriminator wants this maximized. The generator wants this minimized. And that's the loss function. Hopefully this exercise helps in giving everyone some intuition of the loss function in Gans. So we did a few other things. On Monday, we found what the optimal discriminator looks like. So we basically say that the output of the discriminator, if we fix a generator, the output of the discriminator is the ratio of the chances or the probability of data belonging to the actual data distribution divided by the sum of the probabilities of a data point belonging to the generated and the actual data distribution. I see question, can we switch? Yeah, so the question in chat was, can we switch the min-max order? And it was also answered in chat by another person that we have to train the discriminator first. So that's right. So yeah, again, so this hints towards the GAN being an implicit distribution model. We're not modeling the individual probability distributions, but this ratio. The optimal generator, if we input the optimal discriminator, we first train it, we find the optimal discriminator. Sorry. Yeah, so we first train it, we find the optimal discriminator, and then we put it back in this loss function. And what we find is that what the generator is doing is it is trying to minimize the Jensen-Shannon divergence between the generated distribution and the actual data distribution. And that gives, in my opinion, a beautiful interpretation to what the generator is doing. We have two distributions. We want one to look like the other. And under the loss, under the value function, under the objective that we defined, and you guys came up with, what the generator is doing is it's trying to minimize the divergence, the Jensen-Shannon divergence between the real and the generated data distribution. So that's what's going on in GANs, something we looked at last week and something we began discussing also last week was the min-max stationary points, and that we saw in the previous couple of slides, we saw that the stationary points exists, but it's not necessary that the generator would and GANs in general would be able to reach the stationary point. GANs in general are known to be very brittle to training. They need not always converge to the stationary point. There are oscillations, there are other things that happen, mode collapse, they might overshoot. And those are some issues that we'll discuss today. So yeah, before that, I would like to stop here and see if anyone has any questions. But I see a question in chat as, what's the difference if GANs if we used scale divergence instead? Well, we'll look at it a little, we'll touch upon this a little later in the lecture today as to how the different distance measures cause difference in performance. Something I can say right now is you've all studied BAEs, and BAEs are minimizing scale divergence between two distributions. GANs are minimizing the Jensen-Shannon divergence between two distributions. And I'm saying that GANs are better than BAEs. So maybe that says something about the distance measures being used. But we'll look at this in more detail later, especially when we're discussing WGANs and the distance measures in general. It's a good spot, are the important factor here. What stops the discriminator from being from memorizing the whole real data distribution? Another question, other than not giving it all. So we're never giving it. So it's a binary classifier. We're giving it data that belongs to two different classes. And I'm not sure what you mean by the discriminator memorizing the whole real data distribution, except that it's kind of doing that. It needs to understand that a particular data belongs to our distribution, and there is some amount of data that is being generated by the generator. Okay, there's another discussion going on in chat, but I think I'll move on. Let's look at some of the some optimization issues that we see in GANs and some practical issues that we see while training GANs. So one of the questions I think that's very natural to ask is, why is there no static optimal discriminator? Why do we train the discriminator again after we train the generator? And the idea behind this is that the discriminator indicates the direction in which the generator should move relative to where the generator currently is. And again, by definition of what the discriminator is doing, it's outputting the ratio of the probability of data from being the actual data distribution divided by the sum of the probabilities of it being from the actual and the generated data distribution. The generated data distribution has now changed, so your discriminator should change for the generator to still be minimizing the Jensen channel divergence. So that that is something that comes straightforward from the proof. Another way to see this is that if we have a fixed discriminator, what the generator will learn is to produce the sample that is the most likely to occur in the real distribution, and it will basically take an argmax over the dx, and it will do that for all z, and that's not something that we want. So we cannot train the generator first without training the discriminator, and we cannot train the discriminator only once and just keep improving the generator, because neither of those things will be able to do the job that we want done. The causes, there are certain causes, many causes of the optimization issues that we see. Simultaneous updates are required, and a careful balance is required between the two players. Stationary points exist, but there is no guarantee of reaching them.
So Akshat, the Gladys wants a clarification of the first bullet.
Yeah, in this slide. Which slide? No, previous slide. Okay, the discriminator indicates the direction in which the, so it's more of an intuition than anything else. That as I said before, that the discriminator's job is to in some sense guide the generator, and to do that it has to understand what the generator is doing right now. A mathematical intuition would be that the discriminator outputs this ratio, and to be able to do that, it needs to have an understanding of what the generated distribution is, which is for that, which is kind of where the intuition is coming from, that it needs to understand what the generator can do at the moment. Something that you can think of from in terms of the loss function is that the discriminator kind of provides how wrong or right the generator is. And to do that, it needs to be trained on the data that the generator produces. I think nothing very deep here, just building on the intuition that we were talking about earlier in the lecture. Does that make sense? Okay, awesome. Yeah, so again, this is point is, but there's no guarantee of reaching it. If the discriminator gets overtrained, it guides the generator in the wrong direction. If the discriminator is undertrained, if the discriminator is undertrained, it is not a good guide to the generator. If the discriminator is overtrained, it's too hard for the generator to make much progress. And we look at an example that kind of shows how in two-player games we don't want one of the components to optimize itself like completely, and that could be a cause of oscillations and not reaching a stable a stationary point, which is in GANs usually not stable. There are different factors that affect the adversarial balance here. If we use different optimizers, learning rates, batch size, it could lead the two components to be at different points. Different architectures, depths, number of parameters that we use to train these networks also affect that. Something we can take care of is training the discriminator and the generator for different number of epochs. For different number of epochs, different number of iterations, there is usually some, so it's again something, it's more of an art than a science. There are some usual things people use. Maybe we train in the ratio of 5:1, 1:1 also works for very simple problems. Like I think I worked with a couple of data sets where we train both the generator and discriminator for 1 epoch each, and it worked fine. People train the generator sometimes for 5 epochs and the discriminator for 1. 2:5 is also a ratio I've looked at it somewhere. So all these different things affect the adversarial balance in some sense. And to understand how this
The
effect
question
could
from
be taken,
Manish.
at what point should we stop training the discriminator? Yeah, that's, again, as I said, it's more of an art than a science, and different problems would require different, well, there's no right answer, basically. Usually the discriminator learns faster than the generator, so we don't have to train the discriminator too much. And as we go along the process of cyclically training the discriminator and the generator slowly begins to learn. So yeah, there's no right answer. Usually we train the discriminator less than the generator. 1:5 is, I think, a common ratio that I've heard of. Train the discriminator for 1 epoch, train the generator for large amount of time at every iteration. Yeah, so let's look at this example. Hopefully this shows how overtraining can in cases lead to oscillations. So this is the example that Ben gives in his lectures, and I think it's a very good example that gives an insight as to what might be going on in two-player games. So let's look at case 1. So let's say I'm playing rock, papers, and scissors with a probability of me outputting rock is 36%. I play paper and scissors with the probability of 32% each. So what do you think would be your optimal strategy? You want to increase your chances of winning. So what would be your best strategy against a player like me who's doing this? So I see Stefan says, and Justin says, and a lot of other people say that pick paper all the time. And yeah, that's absolutely right. Pick paper 100% of the times, and your winning probability would be 36%, and that's the best you can do. So let's talk about this case. Case 2, where I am a perfectly unbiased player. I'm playing rock, papers, and scissors with equal probability. What would be your optimal strategy, and what would be your probability of winning?
So Clay has a question.
Yeah, Clay, go ahead.
Yeah, so my question is actually from the previous slide. So what do you mean by train only the generator? Does that mean that we're setting the loss of the discriminator to somehow 0 and only caring about the loss from the generator?
Which slide?
Like, for example, when we talked about like the how we want to train GAN and how we want to first train the discriminator and then later on train more the generator. So I'm just asking how we can achieve that in a single iteration. Like, what do you mean by train only the generator, for example?
So by training only the generator, we generate a certain number of samples from the generator, and then we send them to the discriminator. We make the discriminator classify those samples incorrectly. So all that means is that generate more samples, send more samples to the discriminator, and get feedback from the discriminator, get that loss that you backpropagate in the generator for larger amount of samples than you would do in some sense when you're just training the discriminator. Does that make sense?
Yep, I'll think about it. Thank you.
So going back to the question, so when I'm a perfectly random player, what your optimal strategy is? And I saw a bunch of answers on the chat is pick anything randomly. Yeah, any strategy that you choose is optimal, and your probability of winning is always 0.33. And that, in some sense, is a stationary is a point that we want to reach in the game. It's for both players. That's the global optimum in some sense, is to play if both players play are absolutely perfectly random. That's the global optimum of a game of the rock paper scissors game. But let's say I am player A who plays with 0.36. I play rock a little more with 36% probability. So if that's the case, and if we let player B optimize all the way, then its optimal strategy, as you guys said, would be to always go with paper all the time. That's its most optimal strategy if it optimizes all the way. But seeing that player B is doing that, we're in a two-player game scenario. What player A will do is, now that player B is playing only paper, it will now start only playing scissors. But now seeing the player A is doing that, player B will now only play rock, because why should it play anything else? And seeing that player B is now only playing rock, player A will now only play paper. And this just keeps going on and on and on. And this is, in some sense, shows what's wrong with optimizing one of the networks all the way. We end up in states of oscillations. An ideal way would have been like if I was playing paper with 36% probability, player B should have increased its chances of playing paper a little more, and so player A would have increased its chances of playing scissors a little more, and then player B would have increased its chances of playing rock a little more, and everybody would have stabilized to the optimum of playing both things with 33% probabilities, all the three things with 33% probabilities each. So this was kind of an example of how oscillations can occur in GANs. Another common thing, or oscillations occur in two-player games in general. Another common thing we observe in GANs is called mode collapse. So what happens in mode collapse is that the generator learns to generate like a small subspace of the actual data, but not cover the entire data distribution. For example, if you're working with MNIST images, it will start generating only once. like all ones or all twos or all threes, not all the other numbers. Now, when the discriminator sees this and when the loss is propagated when we're training the generator, the discriminator has no reason to call what the generator is doing in that the generator is not doing its job, because even though it's generating a small subspace, it still belongs to the real data distribution. It's still getting good at it. And once the generator kind of starts generating the small subspace, then it has no incentive to generate the remaining digits in MNIST. And that's like something we don't want. That's something that's called mode collapse. I'll show you this video really quickly of how and when we see this happening. So this is the outputs coming from the generator as the generator trains. So we see it's doing a poor job, but it's generating everything. And at some point, it's now not generating all digits, but focusing on 8s and 1s. And, and then it's slowly started to generate all 1s. And if we send this output to the discriminator has no reason to classify any of them as being fake. All of them are being classified as real because they look like 1s. And so the generator has, the loss is very less. The generator is not learning too much because the gradients are very small, but it's still not doing, it's generating real looking data, but it's not covering the entire space that we want it to cover. And that's one common thing that we observe while training GANs. So that was some intuition behind the training issues that we see in GANs. And there are different techniques we use for stabilizing GANs, GAN training. Some of them were discussed in this paper called Improved Training Techniques for GANs in 2000, that came out in 2016. And we'll go through that. Before that, if I'll stop for any questions if you guys may have. Yeah, I see a question is that how do we cope with mode collapse in GAN training? Yeah, so I'll discuss one of the ways which was proposed in this paper as well. So that's coming up in this section. I see another question. What do we mean by adversarial space in GANs? I am not sure what that means. Viksha, do you know what that means? Adversarial space in GANs?
I'm not really sure what this means. So when there's mode collapse, the discriminator works just fine. Because if, for example, the MNIST generator only generates 1s, and then it does a perfect job of generating 1s, the discriminator gets full. So because it's a perfect job of generating 1s, it's just that it never generates 2s, 3s, 4s, or 5s.
Yeah, and hence when we're training the generator, the loss is very low because the discriminator thinks the generator is doing fine, but it's not doing its complete job. And so the losses are low, the gradients are low, the generator is not learning anymore. And so if it gets stuck in the region of just generating samples from a small subspace of our desired data distribution, then it just ends up being there and gets stuck. So yeah, I think there are no more questions, and in the interest of time, I want to get to Wasserstein Distance. I will just discuss some of these techniques that people use. This was a relatively old paper, so some of these are still used, some of these are used across domains, so not just images, but other domains like speech and NLP as well. Feature matching is not one of them, though. Feature matching, what they say in the paper is that that every so the discriminator is in some sense outputting the statistics of the real data, and the generator is trained to minimize the L2 between the real and the generated data. The discriminator is trained at every layer to produce the same statistics that the discriminator would. So the generator is trained at every layer to produce the same statistics that the discriminator would produce for real data and for the generated data. And in this case, we're kind of minimizing the L2 between these expectations. Mini-match discrimination, that's one of the things proposed by this paper to counter mode collapse. So the reason mode collapse occurs is, sorry, one second. So the reason mode collapse occurs is, well, we know why it occurs, but from the perspective of the discriminator, what's happening is that the discriminator is not able to recognize mode collapse because it's looking the images produced by the discriminator from the generator one at a time. So it has no reason to believe that the generator might only be generating all once, because it is only looking at things one at a time. And that's what mini batch discrimination does, is that in the mini batch that you take of generated images, what the discriminator here is doing is that we put in some transformation, a tensor transformation is used, and what happens is that the discriminator makes its decision by looking at all the images in the mini batch and not just one image. And it's not as simple as, you know, taking the mini batch and all of them being processed parallelly, because although all of them are processed parallelly, they're still being processed one by one. It's just that we're using parallelism to do that. It's not basing the decision by the discriminator for one image is based only on that single image. But in mini-match discrimination, that's not what happens. It's basing its decision by looking at all the images in a mini-match. And that, in some sense, promotes the generator to add variability in the images that it produces, which is how this technique kind of discourages mode collapse. Another thing that's used is historical averaging, not used as frequently. It's a regularization term so that the parameters don't oscillate, and we want the updated parameters to be near the moving average of the parameters that we have in Gans. One-sided label smoothing is another. It's a very common thing. Actually, it's not specific to Gans. It's a very old regularization method, and in fact, something you don't have to restrict yourself to with Gans. You can use them in all kinds of classification problems that you work with. The idea here is to not use zeros and ones as labels, one-hot vectors, but our targets can be 0.01 and 0.99, something like that. So it is a regularization method, prevents overtraining, and the sigmoid is not saturating, and it in general smooths, and it does not let, again, the discriminator overtrain, and we see better performance with one-sided label smoothing. Again, something that's used very commonly. Virtual batch normalization so came around the time that this paper came out, 2015, 2016. And it's also something that we use very commonly in Gans now. It's so how this is different virtual batch normalization from the usual batch normalization is that we kind of picks a batch of real data and we collect statistics of the shift and the scaling that's done in batch normalization over this fixed batch of real data. And that's kind of what we use to do batch normalization for any mini batch that we use in GANs. So these were some of the methods that people use for GAN training and stabilization. And let's now move to a very important topic, I think, Wasserstein Gans. These are something that have become default GANs that people use these days. So nobody uses the original GAN formulation. Everybody uses WGANs, not even WGANs, but WGANs with creatine penalty. And this kind of touches back to a question that somebody raised about KL divergence and Jensen Shannon divergence and what's the difference. And we'll touch upon that in this section. So the reason so whenever I see this spelling, I spent a bit of time in Germany before coming to CMU. So my instincts tell me to pronounce this in German. So how you would pronounce it in German is Wasserstein. But is there an English pronunciation to this word, Bhiksha?
It's going to be Wasserstein, right?
Wasserstein. Yeah, it's like yeah.
Wasserstein is the German pronunciation. It's a W and a st instead of st.
Yeah, I have two competing things at this point. I don't know what I'll call it next. But yeah, so let's get into a bit of the intuition behind Wasserstein Gans. Sorry, and the reason they're called Wasserstein is the metric that we use here, the Wasserstein distance. It's again a metric that's used to calculate the distance between probability distributions. So a way to understand it intuitively is, let's say we have two distributions and we represent the two distributions, each of the distributions, as a unit amount of earth or soil. And the Wasserstein distance is the total, is the sum of the mass times the mean distance it's required to transform one distribution to another. It's like intuitively what this means is that, let's say one of our distribution is here represented by the red points, one of our distribution is the blue points, and we want to transform the red distribution to the blue distribution. And to do that, a way to do that is to move all the points, all the red points to the blue points, and the mean distance in some sense to make this transformation from the red distribution to the blue distribution by moving individual points in some sense is the Wasserstein distance. Mathematically, what this looks like is we want to calculate the expectation here where of x minus y. So there are different metrics that are used in calculating the Wasserstein distance. It's the so to be able to shift the red points to the blue points and calculate that distance, we need some distance metric to measure the distance between the red and the blue points. It could be L1 norm, it could be L2 norm. What we use in WGANs is L1 norm. So the distance between X and Y is measured using L1 norm, and that's what if you read the WGAN paper, you'll see Wasserstein 1 distance, which is basically, which means that L1 norm has been used to calculate the distance. We want to find the mean distance between the reds and the blue points so that we transform the red distribution into the blue one. Now, let's see what this kind of means. The infimum term. So we want to, again, convert the red distribution to the blue distribution. Now, one way to do it is like send this red point to this blue point, this red point to this blue point, like exactly the way it's shown. Send all these red points to blue points, calculate the x minus y's, take the average. That's one option of calling that the Wasserstein distance. Another option could be I send this red point not to this blue one, but to this blue one. This red point not to this one, but to this one. So now there is a completely different option, which is called transport plan. And this gamma is basically representing one of the ways of doing that transformation. And in this new way of doing that transformation, if we calculate this x minus y and take expectation over it, that's another option that we could call the Wasserstein distance. The infimum here is that we take the minimum of all these options. So we have lots of options of transforming, or lots of ways of transforming the red distribution to the blue distribution, called formally as the transport, different transport plans, and we choose the value that's the minimum out of all the possible ways we can do that. And that is what we call the Wasserstein distance. It's a true distance. It has all the, it satisfies all the properties of distances, symmetric, triangular inequalities, and all that good stuff. And I guess the question you should ask is why should you care about this crazy looking distance? And this kind of relates back to a question that was asked initially, is that the entire game we're playing here in VAEs and GANs is the game of distance measures. So we used to use a divergence metric for VAEs, and that was KL divergence. In GANs, we minimize the Jensen-Shannon divergence between the actual data distribution and the generated data distribution. And in WGANs, we minimize the Wasserstein distance, which is another distance metric. And the difference in performances and the stability of training in some sense attributes to the different distances we're using. And if I say that VAEs are better, GANs are better than VAEs and WGANs are better than GANs, I might be implying that the distance metrics that we're using are better than the other. And let's kind of, in the next few slides, I try to give an intuition of why that's the case. Yeah, so let's start with KL divergence. So we'll try and calculate the KL divergence between two of the simplest probability distributions. The first one is, so the distributions are just two peaks with at one px having a peak at x equal to 0, qx having a peak at x equal to 1. We want to calculate the distance, the KL divergence between the two peaks. Let theta be the distance between the two peaks. Now, if that's the case, if theta is not equal to 0, so regardless of how far apart these peaks are, the KL divergence between the two distributions will always be infinity. You can do the math. It's very trivial. You just use this formula, use summation instead of an integral. The distance between the two peaks, whatever it might be, if it's not 0, the KL divergence is going to be infinity. If it is 0, the KL divergence is going to be 0. So the KL divergence, although it does indicate to us when the two distributions match each other, when they do not match each other, it's not giving us any useful information as to, we don't know if the distributions are 10 units apart, 20 units apart, 5 units apart, because in all the three cases, the KL divergence would be infinite. And another thing to look at is like, it's not differentiable with respect to theta, which is the distance between the two peaks. The next measure that we use, and something that we use in GANs, is the Jensen-Shannon divergence. Let's calculate the Jensen-Shannon divergence for these two cases. Again, theta is the distance between the two peaks. If you calculate the GST when theta is not equal to 0, then the Jensen-Shannon divergence is log 4. If they overlap, the GST is 0. So this in some sense is better than GANs because our entire thing does not blow up like crazy. But again, the same problem still persists. If the distribution, if the peaks are 10 units apart or 20 units apart or 5 units apart, we don't get that information by calculating the Jensen-Shannon divergence, because for all of those cases, the value would be log 4. And if only if the distributions overlap, the value would be 0. So the minimization point is correct for both KLD and GST, but when they do not overlap, we have very little information to work with. The Wasserstein distance, on the other hand, if we have these two peaks of distributions, there aren't too many transport plans. There's only one thing you can do to convert one distribution to the other, and the Wasserstein distance in some sense depends on the distance between the two peaks. So in this scenario where we're taking L1 norms, it turns out to be the absolute value of the distance between the two peaks. And it's differentiable with respect to theta. I mean, the further apart they are, the larger the distance is. The closer they are, the lesser that is. And that in some sense gives us information as to how good or bad we're doing in bringing the two distributions closer together. And that's exactly the intuition behind why one distance measure might be better than the other. The GST here, so this is a plot showing what we discussed. The plot here on the right is the GST. We can see that the value is a constant. If theta, so theta is again the distance between the two peaks. We can see that the value is a bunch of constants until theta is 0. When theta is 0, the value is 0. And when theta is again greater than 0, the value is again a constant. So if we're in one of these regions, there is no way for us that we can reach theta equal to 0. Whereas in the case of Earth mover's distance, the Wasserstein distance, we have an incentive to reach the point theta equal to 0, which is exactly where two distributions overlap. So this, in some sense, shows how one metric might be better than the other. The distance value is not constant for non-overlapping distributions. It's differentiable with respect to theta. And those are two very good properties that we want our distance metric to have. And this is exactly what's used in WGANs. We have changed the distance metric that we're using to translate one distribution, the generated distribution, to the other. Now, I also saw a question in chat as to, isn't it like crazily difficult to calculate the Wasserstein distance? You probably need n factorial. Well, there are lots of ways to do it, probably not n factorial. But again, so using the Kantorovich-Rubinstein duality, what the authors came up with is, and this is something that's beyond this course. I don't pretend to understand it completely myself, but what they came up with was a loss function for the generator that now minimizes the Wasserstein distance instead of the Jensen-Shannon divergence. So if we use this value function, this objective in GANs, instead of the one we kind of came up with at the beginning of the lecture, the generator would essentially be minimizing the Wasserstein distance instead of the Jensen-Shannon divergence. And that kind of makes all the difference. And if we just look at what's going on here, all that's gone is the logs are gone. The 1 minus term is gone, but we have a minus sign outside. It basically means the same thing. And this formulation, in some sense, when we train the generator with this formulation, it's now minimizing the Wasserstein distance. And the claim is that doing that is better than minimizing the Jensen divergence. A constraint here that needs to be put on the discriminator is that the discriminator should be a one Lipschitz function. And does anyone know what a one Lipschitz function is?
Is it like Lipschitz continuous for the first order, something like that?
Yeah. It exactly what you said. It's Lipschitz continuous, and the derivative at any point should not be greater than one. And that's so K Lipschitz means that derivative at any point is not greater than K. So the condition that it needs to be put on the discriminator, which is again a differentiable function, is that it should be one Lipschitz. And the way that it's done in the original formulation, which is why it does not work as good as its successor, is that what they do to enforce this condition is that they restrict the weights by weight clipping. So what they do is they restrict the weights between minus C and C. And so it does not guarantee that the discriminator would be one Lipschitz, but it does guarantee that the discriminator would be K Lipschitz for a certain value of K. If C is known, if you give me the C, I can tell you what the K would be. And so there is a mapping between this C to K. And that was their way of making sure that T should be a one Lipschitz function, and that it follows the constraint put on the discriminator under this formulation of WGANs. This was a nice improvement on GANs. It had a theoretical justification of why a particular distance metric was better than the other. But in practice, the results weren't as good as people wanted. And so what's the standard GAN that people use these days is WGANs, but with a gradient penalty term. This paper, again, so WGANs came out from the Courant Institute at NYU. This, again, was paper from people from the same group working on it. And here, the way they enforce the one Lipschitz constraint is different from the way it was done in the original WGAN paper. What is done here is that instead of putting a hard constraint that was put in the original WGAN paper, they add a regularization term, a softer constraint, which they call the Creatine penalty. And this constraint, in some sense, forces the gradients to be at most one everywhere. So something to notice here, although I really want to get to the next section, but the X here is different from the X that's in the original loss. So as we know, the first term X belongs to the so in the first term, the X belongs to the generated data distribution. Here, the X belongs to the real data distribution, but here the X belongs to a different data distribution. And that in some sense is, this X is a point lying on the straight line between the generated and the real data distribution. And those points are randomly sampled to calculate this gradient penalty term. So you're not calculating, you're not trying to minimize, you're not trying to restrict the gradient of the discriminator at all points in space, but at random points between the generated and the actual data distribution. And it turns out that's usually enough for GANs. And that's also our region of interest, because that's the distance which we're trying to minimize. And this in practice works a lot better than the original WGANs formulation. For more details, I refer you to the WGAN GP paper. It's called Improved Training for Wasserstein Distance. It's a very easy read, and actually there isn't much else except for what I said, but I think it's a nice paper to go through. With that, and yeah, again, just reiterating the fact that it's the gradient penalty is a softer constraint than weight clipping that was used in the original Gans formulation. So before we end, I'd like to go through certain important GAN architectures, and then I'll stay back and take any questions we have at the end. There are still 5 minutes that we have, and I would really like to cover conditional GANs, which in some sense form the basis of lots of cool applications that people use GANs for. So this is what's kind of been going on in GANs. The image quality has over the years gotten better, and let's see how that happened. So the original GANs paper came out in 2014. A paper that followed the original paper very soon was the conditional GANs paper. It was roughly the same people working on the conditional GANs paper as the original paper. What they do here, it's a very simple idea, and it's something that's used in a lot of applications of GANs, from image-to-image translation, text-to-image synthesis, and a bunch of other things. This is exactly the same loss function that is used in the original GAN formulation, but the only difference here is that the inputs are now conditioned instead of, so basically the inputs are now conditioned. Instead of giving the discriminator an image, we also send in a vector which kind of accounts for this conditioning. So the way it translates into practice is that in the generator, we're now sending, instead of just a vector from our chosen prior space, we're sending in a vector that represents something. The idea here is that we're using GANs to generate, let's say, MNIST images, but we have very little control, or in the original formulation, we have no control of what it is that we're generating. With conditional GANs, we get some control. We use, for example, let's say we're talking about MNIST images, we condition the generation on another vector, which for MNIST images could be one hot, and let's say we have one hot vector representing each class of digits. So now the generator, in some sense, learns to produce images conditioned on the input one hot vector as well. We also condition the discriminator with it, with the same vector. There are two formulations of conditional GANs where two papers came out around the same time, where in one paper the conditioned vector was combined with the input and then sent into the network. In the second formulation, this conditioning was done at the output of the discriminator just before making the softmax decision. Both work fine, but the idea remains. We want to get more control over what we're generating, and to do that, we condition our generation on an input vector. And it has lots of cool applications. Image-to-image translation is something that is based on conditional GANs. So I see a question as to, I'm not sure I understood what conditioned vector means. Yeah, it's just like we're conditioning probability distribution. So in the formulation, this is what it looks like, that we're conditioning the generation process and the discrimination or the classification process, not just based on the input, but also another kind of input which we now have control over. In practice, this is done by sending in a one hot vector to the generator, which we choose. So mathematically, it's conditioning, but in practice, it's just concatenating another vector, which for the case of MNIST images could be a one hot vector corresponding to the different digits. And conditional GANs have lots of, they're really important in image-to-image translation and all the cool applications that you see of changing domains of images, like converting a male looking like face to a female looking like face. StarGAN was one of the important papers which kind of did multi-domain image-to-image translation, which was not possible before this one. And all of these cool applications kind of come from conditional GANs. It's a really easy concept in some sense. It's a really one of the easier extensions to GANs, but I think one of the more powerful ones. I wanted to go through the GANs progression, but I think we've run out of time. So I will stop here and feel free to ask any questions that you might have.
Any questions, guys? If not, I will stop the recording.